on the YouTube. We have a really cool program today. I'm really excited about it. I've been lucky enough to be a part of VISxAI in some capacity for the past 5 years, and I'm particularly excited about this one, so it should be a good one. For those of you who don't know me, I'm Angie, and Fred, Alex, and I have been the people behind VISxAI this year, but really none of this is possible without our program committee and our reviewers and all of you who submitted. It's no small feat to make an interactive visualization, never mind one that is deeply explaining an ML concept. So we are greatly appreciative of everyone who worked so hard to make this all happen. This year actually marks the 7th year of VISxAI. And our goal as a workshop has always been to be a non-traditional place. So we don't accept papers, we accept interactive visualizations that explore and explain AI concepts. And then we invite really interesting keynote speakers and bring a community together and spend the day together. What I think is really remarkable is that, when Hendrik started this and others back in 2018, this was the goal. But I think that this goal of using visualization to explain AI models is maybe even more pertinent now, as we have models that are bigger and more complex and more widely deployed than ever. So today, like I said, we have a really exciting program, some administrivia. Please join our Discord and Slido channels. We're going to be taking questions via Slido. If you are in the room with me, you're also welcome to ask your questions out loud. We're going to start with an opening keynote from David Bao. Then we're going to have our first set of lightning talks, a break, our second set of lightning talks, and then a closing keynote from Adam Pierce. And then you'll hear from me again, and we'll give out some awards and send you off for the rest of your day. So, without further ado, I'm pleased to kick off our session by welcoming David Bao as our opening keynote speaker. David is an assistant professor of computer science at Northeastern Korea College, studying the structure and interpretation of deep networks. And for me, what I admire most about David's work is how he's improving interpretability from multiple different angles. He's not only developing rigorous interpretability methods, but he's also thinking deeply about how humans will interact with those interpretability methods. And as if that wasn't enough, he also works on open source interpretability packages that empower us all to better understand our models. So please join me in welcoming David.
So I need sharing access.
Yep.
There we go. Computer audio. And I'll turn up my volume here. So in principle, I should be able to hear what's going on. And then let's see here. Okay. So welcome to Florida. Yeah, I was just chatting with Angie that it's kind of amazing the world that we live in for organizing meetings today, because it sounds like, after St. Pete's was canceled, the team scurried around and found an alternate venue in Tampa, just perfect, just in time for the second hurricane. And then when that didn't come through, I got this note from Hendrik saying, Harvard, we're on. And it's kind of amazing. I think it's an example of resilience. I think that the whole academic conference community is a lot more resilient now after the COVID experience. There's no canceling this conference. The show will go on, and it's amazing. And so I thought actually this would be a good topic for the talk. I was originally thinking, hey, let's talk about how do you visualize AI? But I think actually it's a good moment to think about what's needed for resilience in AI, because it's not just hurricanes that we're sort of setting up our society to be fragile too. But technology too. And as AI gets widely deployed, I think this is one of the major issues that's going to confront us. Probably not in the too distant future. How is society supposed to respond when we wire up all of our systems with extremely complicated and sophisticated and powerful AI systems? What should we be doing to make sure that society remains resilient as we potentially make it more fragile to these kind of things? So the hurricane thing is really an inspiration. Now resilience is about ecosystems. It's not really about just the technology itself, right? And it's about how the whole ecosystem can adapt to unexpected challenges. And so I want to give a little story of technology resilience that affected me a few weeks ago this summer. Um, how many of you were aware of, or how many of you know what the Counter-Strike disaster was? Do you know what the Counter-Strike thing was? No. The not what's it called? Not Counter-Strike. What is it called? CrowdStrike. CrowdStrike. Who knows what the CrowdStrike is? Not Counter-Strike. Counter-Strike is like a video game, isn't it? Yeah. I've been talking to my teenage son too much. So yeah, the CrowdStrike disaster. So for me, the CrowdStrike disaster affected travel. I was actually in a plane crossing the Atlantic Ocean and woke up in the morning, the pilot turned on the lights, woke up everybody and says, welcome everybody to Europe. As you've been sleeping, there's been a global cybersecurity incident. It was kind of like 9/11. All the airports are closed. Your connections are canceled. We're trying to see if we can land at the airport and so on. And so I got stuck in Zurich with no ability to take any transportation out, and booked a last minute a hotel stay at the airport Hyatt Hotel. And this was the scene at the Hyatt when I arrived. The entire lobby was actually, I didn't take a picture of all the people on all the couches. Usually there's this empty couch area in the lobby of the hotels. Like instead, it was like refugee crisis center. Every horizontal surface was full of somebody in their suitcases and everything. And I thought, oh my gosh, you know, every flight is canceled. Everybody in Zurich is looking for a place to stay. So I'd already booked my room, as soon as I heard everything was canceled. So I went up to the front desk and they said, sorry, we don't have your reservation. And what had happened was this CrowdStrike crash had not just killed all the airlines, they had killed this system called the Opera Hotel Property Management System, which is what Hyatt happens to use to manage all their hotels. And so let me give you examples of things that Hyatt couldn't do on that day, right? They couldn't look up my reservation, right? They couldn't charge anybody for rooms, right? They couldn't even open up the doors to the hotel rooms. They couldn't, process payments. They couldn't figure out where their employees were. Their little employee address contact book for calling everybody in for emergency wasn't working. They couldn't pay anybody. They couldn't control the heat or the light. Basically this amazing system, controlled every aspect of the hotel, and it happened to run on Windows, and it was down. And so then I realized why the hotel lobby was so full, because all the hotel rooms in the hotel were empty and all the guests were sleeping in the lobby. So I left my suitcase there and I was in Zurich. So I got a nice tour of the chocolate factories, and I figured I'd come back, in the evening, and they probably had it clear by then, right? So I got back in the evening, and it was sort of an interesting story about the resilience of the hotel, and I'll tell you that in a minute. But I want to define what resilience means. So there's really three types of reliability that we talk about when we have, complicated systems. And so you can think of it as three R's, right? And so the first R is reliability, regular reliability, which is like reliability and expectation. It's the kind of thing that machine learning people are expert at, right? They take the average behavior and they make it better, right? And so and we do this in the real world a lot. Like even Hyatt does it when they choose to continue to run their Opera system. They have 20 years experience running it. They know exactly how often it's up and how often it's down, how reliable it is. So they continue to hone their operations. In the average case, they know that Opera is extremely reliable. Now, there's a second R, which is robustness, which some people think of as sort of worst case behavior. It's really worst anticipated case behavior. And what robustness is really about is figuring out what the vulnerabilities of your system are, and trying to prepare for that in advance. And so, the common vulnerability nowadays is like adversarial attack, like security fit systems. And so you can go to the Hyatt website and you can see, have you patched Opera? And yes, and actually in 2023 there was a vulnerability that was discovered. CVE 2023-2193 has been patched. We're all up to date. We've done our red teaming, right? And our system is as robust as we can make it, right? And so in AI, we do the same thing. There's actually people in AI who are very focused on red teaming, and trying to figure out how to jailbreak systems and how to protect them against jailbreaking and all sorts of other attacks and cat and mouse game. Okay, so what is this third R? What is resilience? So resilience is about the stuff that you weren't able to anticipate, right? Which is, the unknown unknowns, right? The other stuff, right? Right, Donald Rumsfeld's will never die. Um, and so uh, and so it's about response to unexpected challenges. So, for example, even though Opera is totally patched, it could still cause a problem if something unexpected happened. Actually, it was the patching system itself that brought it down. And people didn't anticipate that. So, but resilience would be able to say, if you were able to say, with Opera down, our hotels keep on running anyway, right? And so I'm going to talk a little bit about resilience because I think that it's very relevant to what we do in this room and in this workshop, because I think that in AI, to get resilience, it's really about the interaction between humans and these complex systems. You need human understanding, control, and power, and those would be the three themes. And so let me illustrate with this hotel. So I got back from the chocolate factory, and the lobby was emptying out. There was just one line up to the front desk, and it was great. I thought, they've got Windows running again. Certainly it's not that bad. But actually, when I got to the front desk, I said, can you look at my reservation now? Take my credit card, all this stuff. And they said, no, the system is still down. We have no idea when the system's up. I said, where did everybody go? Did you kick them out? Am I going to should I go down to the Motel 6? And they say, no, we're running the hotel anyway. And so we're show us your email of your reservation. We'll take that as proof that you have a reservation, right? And then we need it. So, but it looks like on your email you haven't paid. So we're going to take a credit card swipe. We're going to swipe you in the restaurant, right? And then I said, okay, fantastic. You got me through, right? So give me the room key. Let's go up. And they said, oh, no, no room key. And I said, well, so what did I just pay for? They say, follow Max here. Max will let you into the room. He has the maintenance key to all the rooms, and now he knows who you are. And I say, so well, what happens when I go to dinner? He says, well, Max knows you, so find Max, and he'll let you back into your room. Right? And so now, so the hotel was able to do this because they had three things, if you think about it, right? One is they had all the essential functions that they had lost due to Opera. They understood what they were. They understood they had to get people into rooms. They understood they had to do credit card swipes, right? And so understanding what they had to replace was essential for resilience. And then the second thing that they had is they had figured out they had technical control over these functions. So even though they couldn't get the room, electronic key open, they realized they had the maintenance key that they could use to open up all the doors. And that was enough control for them to do all the things that they needed to do. And then really importantly, they had permission and power to do this crazy thing that they were doing. So because think about all those credit card swipes, right? If somebody comes and says, "Oh, I've already paid," they get a free room. Somebody has to make a judgment call about whether it's okay to take a payment or not. And so, it's a leap of faith for the executives to say, yeah, the hotel front desk staff can do that. And so giving this kind of permission was also essential for getting the hotel up and running. So isn't that amazing? So, but let me tell you, staying in that hotel that night was actually pretty terrible. After I got into my pajamas and tucked into bed, half an hour later, you know, um, the room's all dark, and then all of a sudden you hear this weird sound, and it's the heating system of the room in the hotel turning off. And then a minute later, all the lights in the room turned on. And so I got up, I turned off all the lights again, and then 40 minutes later, the same thing happened. And actually every hour, the hotel went through this reboot sequence, where the heat would turn off and the lights would turn on. And it was the most terrible thing. I called up the front desk. I said, "Do you know that this is happening?" And they said, "Oh, yes, sorry, sorry, Mr. Bao. Uh, we have no idea what is going on. We don't know what the system is trying to do." I said, "Can you just turn off the electricity to my room, please? I need to sleep. I need to give a talk tomorrow." Right? And they said, "No, no, no, no. There's no way of doing that. And besides, we've talked about it. Even if we could cut the electricity, we're not allowed to. It's a safety issue. You need to have all the fire alarms going and everything." And um, so yeah, so it's one of the worst hotel nights I've ever had. But they had already taken my credit card swipe. So Um, so okay, so there's three ingredients. There's understanding, there's control, and so let's just run through it. So some people say like understanding AI is implausible, it's hard to do. I think it's very hard. I just want to give you a little sense for the way that we think of understanding. So who here is familiar with the Rome paper? So okay, so I'm just going to run through this really quickly because some of you already know it. But the one of the things that AI does a lot of is it absorbs a lot of factual knowledge, a lot of factual understanding of the world. And so when you normally think of these large language models as next word predictors, but the next words reflect a lot of factual knowledge. If you say Miles Davis plays and tell me what the next word is, it won't just be grammatically correct. It'll also reflect, actual knowledge of the world. And so one of the interesting things that's happened in the last year or two is that we can actually locate where a lot of this knowledge is inside these very large networks. And so the way this works is you can do scientific experiments on the large networks by running them multiple times and transplanting, oops, wrong arrow. So you run them multiple times. So here I'm running it once where it's recalling that Miles Davis plays the trumpet, and the other time the network is poisoned. It's run without the necessary information to figure out the fact, and then we figure out what computation inside the network was responsible for resolving this fact. And one of the ways that you can do it is you can transplant specific data and computations from the first run to the second run and probe around to see if you can find where it is that causes the network to actually have interesting outputs, like to say trumpet again, right? And if you do this, you get these maps over the network that indicate that most places are not very interesting to resolve most computations, but you find these very sparse paths through the network that indicate like where the decisive computations happened. And so you get these surprises. Like the big thing that we're surprised when we're looking at factual recall is a lot of factual recall happens very early in the network, a lot earlier than we thought that it might that might happen. Um, and so if you narrow down what's happening locally, you realize what's going on is that in early layers at early tokens, there's this vector mapping between vectors that represent something like the phrase Miles Davis, mapping to vectors representing things like, somebody who plays the trumpet, a jazz musician, from the city, right? So from the text to the meaning, right? So from just like the bigram, Miles Davis, to what the concept is. And so there's this mapping, and you can do things to localize what it is. And it's really given us the beginning of a roadmap for understanding certain types of knowledge inside AI. That I think that there's a growing consensus that it's really helpful to understand the concepts in a network in terms of the vector representations that are the footprint of those concepts in the network. So, like the text Miles Davis has a vector, or the idea that somebody plays a trumpet, that corresponds to some vector in a vector space. And then you can think of knowledge as associations between vectors, like some input vectors and some output vectors, or some other vectors are associated with each other. So the weights of the network sort of serve to have knowledge by relaying vectors to each other. And then reasoning really is showing up as long, complicated pathways through these kind of connections. And so okay, so sort of as a scientific uh, um, pursuit, we're starting to see what the structure is, or at least some of the structure is, inside these networks. And it's just the beginning of understanding the content of these things. And so one of the challenges to this community here is, can we bring this from sort of abstract scientific findings to something that's actually useful to users? And so I'd encourage you to continue to follow what's going on in the unfolding understanding in this area, because I think there's a lot of opportunities to make this kind of thing useful. Okay, so that's the understanding part. So understanding is like the first thing to try to figure out to get resilience. But understanding is no good if you can't use that understanding to control things, to like open up the hotel room doors again, right? And so let's talk a little bit about controlling AI. So we'll continue with this memory theme. So, I talked about there's this vector mapping functionality that happens inside a lot of neural networks. Um, and so you can kind of think of it as mapping vectors from a concept to a concept. Like, what is a tree? A tree is leafy, right? What is a dome? A dome is roundish, right? What is Miles Davis? Miles Davis plays a trumpet, like from something to what you know about it. And so we've been experimenting with this in a bunch of different settings to see what kind of control we can get by harnessing these mappings. So here's like an example of something that we've been able to do. So I'm not sure if any of you are doing research on the text-to-image diffusion models. I'm not sure, like, any papers on diffusion models here, Hendrik, a little bit. And so, these are really interesting systems because they're so powerful, but they have well-known problems. Actually, one of my favorite conversations from the last few years was when diffusion models were starting to be released. I remember talking to Martin, and he says, "Oh yeah, we have them running inside Google." I said, "How come I can't play with them yet? How come they're not released yet?" And he says, "Oh, I don't know. They're not really quite ready for prime time." And why is that? And the why it is because of things like this. So let me give you an example. So if you ask um, a diffusion model to draw you a picture of doctors, then it will parse your text into a vector. That vector will go through cross-attention maps and so sort of a couple neural network layers that do a mapping into another type of vector, which controls the image generation process. So like what doctors look like, you can think of as being encoded in that vector. And then those vectors will eventually, what happened to my image? Okay, give me a second. Um, I I will find a version of this talk that has the image. Resilience. I can't like
That's not random.
right. I can't like talk about images without showing you images. Okay, here's images. Okay, so what doctors look like? Looks like this, right? Okay, so this is oh, sharing. Okay. Sharing. Ah, how's that? Are we live again? Image. Okay. And uh so what's wrong with this image? Does anybody have a doctor that doesn't look like one of these doctors? Yeah, so like give me an example of like what's wrong with this set of doctors here? They're all men. They all kind of look like cousins. Um, and um, and so yeah, so this is called bias amplification. So obviously the training data, like all training data, has some biases in it, and the weird thing that happens with diffusion models, text-to-image diffusion models, is after you train them, they tend to not just reflect the biases of the training set, but they amplify them quite a bit, and so they're very, very obviously amplifying societal biases here. So all doctors look like this. All CEOs look a certain way. They all look like a certain type of tech bro, and so yes. So how do you fix this? How do you fix this? Well, one way of fixing it is to investigate this mapping, from text that means doctors, mapping to a vector that defines what doctors look like. It turns out that these diffusion models, they do know what female doctors look like. You can ask them, draw me a female doctor, and they'll do that. Draw me a male doctor, they'll do that. But when you just ask for doctors, they don't understand that this should be a diverse concept. And so what you can do though, and this is a little bit of example of the power of vector spaces, is that you can take the VM of what male doctors look like. You can take the VF of what female doctors look like, and then you can say, we don't know what the vector is that represents an equal mix of doctors, but we can hypothesize that it's on the line between VM and VF, and we can do a little grid search and see if there's a vector somewhere on that line that's like an equal mix. And indeed you can. You can find such a vector, and it is on that line. And so actually, so we do that. And once you have the vector of the visual definition that you want, then you can write that directly into the neural network and change its definition of what it thinks doctors look like. You get output that looks like this. Actually, we search over a slightly larger vector space to get racial diversity as well. Right? It makes sense? So okay, so and the nice thing is that this is not slow training data based fine-tuning of a model. This is directly changing definitions inside the model of how it maps one type of vector to another. So it's very fast, it's very lightweight. You can do it in a couple seconds. And so you can do it for hundreds, thousands of concepts at the same time. You can collect together all the things that you want to redefine, and then alter the rules of a model to do this. So we we tested it on its ability to deal with a lot of different societal issues. You've got copyright issues where you've got artists who prefer not to be copied in a model. You've got biases, many different professions that are extremely biased. You've got unsafe content, like offensive content, where a model will like produce nudity when you didn't even ask for nudity, and things like that. And so you can go through the model and redefine the way it thinks of all these concepts. And the nice thing is that the model editing methods are really fast. So rather than this being some year-long process of trying to curate billions of pieces of data, you can do this in just a few minutes, and then you can test what you get, and you can iterate very quickly. So it feels a lot more like traditional control over like traditional software than what we have in machine learning. So I think this is the type of thing that we should we should aspire to and develop. This doesn't work perfectly, so this is an active research area, but this kind of thing. I'll take questions at the end. Okay, cool. All right. So that's an example of control. I think it's really exciting, and it's another thing that we need to figure out how to bring to people. So another call to action. Okay. So the third ingredient is power, right? That giving people permission to do things. And so, okay, what does that have anything to do with like a technology conference, right? Power to muck with AI. And I think that this is actually maybe the most important thing. And I think it does have to do with technology. So I'll talk a little bit about that because, we're sort of creating this unhealthy structure in the tech business where we actually have this opportunity to give people a lot of understanding and control of the systems that we are using and making, but we're not actually giving it to people because there are really two parts of AI. There's this hugely expensive foundation model training that a few companies are doing for $100 billion at a time, or $100 million at a time, right? Um, and it's expensive to absorb all the world's information to a neural network, right? So not that many people can do it. But after you've got a foundation model, it is not that expensive to look into it and to fine tune it and to control it and to customize it to different things. Whereas one of these things is like, $100 million of electricity. The other thing is more like $1,000 of electricity, right? So it's a lot less expensive to do this second stage. And yet, this second stage is really the interesting part. It's the part that defines all the things that we care about in society. And we sort of have this weird structure where the companies aren't really giving us control over the second part. And it's pretty unhealthy. It's this weird, unhealthy power imbalance that's artificial, where we're setting up a structure where we're using $100 million to protect $1,000, where society gets all the benefit from $1,000. Okay, so um so now you might say, well, we've got Meta, right? Meta is like releasing these foundation models. They're putting all this money out, they're giving stuff away, but there's actually this weird situation. So you guys are familiar with Llama 3, 4, or 5B. Who's heard of this model? Okay, that's great. It's like a foundation, pretty capable model. Not quite as good as GPT-4 or whatever, but it's pretty good. How many people have it was released this summer. How many people have been using Llama 3, 4, 5B in their research? Oh, one. Yes, that's great. How do you use it?
I just applied. I'm not modifying, not repeating it.
Yes, exactly. So it's possible to run it by loading it up in a standard inference package. But it's very hard to actually get into it to use it. And the reason is because just loading the model takes like a couple $1 million of capital just to get like a data center that has enough GPUs and adequate networking hardware and everything to run it, because you can't just run it on like a standard like graduate student workstation. And it doesn't matter if you're doing heavy duty training or if you're just cracking open a tiny piece of it to do a little piece of work. It costs the same couple $1 million to get going with it. And this is a massive barrier, even if you have access to the weights to do this. So there's this last thing, which is sort of creating the culture that of permission to crack these things open and to fiddle with them and take control of them, that we're really missing on both the closed side for company policy reasons and on the open side for capital cost reasons. And so I think it's important for us as a community to figure out how to get through it. We've got a technical proposal for how to do it, and I want to invite everybody to use or improve this technology. The idea is that the big company APIs are able to give you access to train parameter models, and the reason that they do that is because they give you inference access, And the reason they're able to do that is because they invest a lot of engineering in what's called inference servers. So when you use the OpenAI API, it's an inference API, and really you're sharing GPUs with hundreds or thousands of other people to make that really economical when you're using an inference server. But when you're doing science on a model, then you're customizing something. You're not sharing this with anybody, so it's extremely expensive and difficult to do. And none of the commercial companies are doing the work to allow you to do the science because it's not in their business interest to do it. So what NDIF is this project to try to do the commercial style work of creating an inference server that's transparent, that gives you access to the internals. And I'm just going to take 2 minutes to describe to you like how it works. It's a PyTorch extension, and the thing that it does is instead of giving you a function that you can call that represents a neural network, you can take any neural network function and you can wrap it in an nsight object, and it turns that function into a context manager. So in Python, that makes it a with statement. And then so instead of calling the function to say, tell me what word comes after the truth is the, which it would normally say, the truth is the truth, right? The language model would just say, the next word is truth, right? Instead of doing that, use a with statement and say, with this function running, with this language model tracing this input, do the following, right? So I'm actually going to, let's do something non-trivial here. Let's grab the 14th layer. Let's get certain neurons. Let's fiddle with their insides. Now, after doing some research, we might say, we have a vector direction that represents the truth. Let me see, what correlates with that vector direction inside the neural network, or we might have a vector direction that, that correlates with gender bias or something like that. Let's take a look at. So you can do all sorts of crazy things inside this with statement. And then the key is when you're inside the with statement, all these tensors that you're manipulating, all these extra actions that you're doing, they're not actually executed on your workstation. They're executed at the end of the with statement when you're done. And if you say remote equals true, then these things will be executed on the inference server. So it's a way of saying, let's have inference together with this computation graph of extra stuff that you want to do that pokes and gives you control over all the stuff on the inside. So this is pretty low level. And one of the challenges is to do the science, to create the interfaces and to create the interactions necessary to take this sort of low level access and make it ordinary and accessible to people. That's sort of my third call to action to all of you. So by the way, in this example, this code here takes 3 neurons, it flips them on. These 3 neurons are the opposite world neurons inside Llama 3 or Llama 2, I guess. And when you ask it for the truth is the something, it'll say the truth is the lie, right? And actually, if you ask it to define anything, it'll tell you the opposite of it. And so it's very interesting to see that there's this negation processing. It's very localized inside the model. And but there's all sorts of really interesting structure and all sorts of interesting things to take control of inside these models if we exploit their access. And so my call to action is to recognize the powerful place that you guys all are in the kind of research that you do. That being at the boundary between AI and humans is really being in the decisive place for equipping humanity for dealing with the unexpected in AI, for creating resilience in the way that we stitch AI into society. I think this is going to be increasingly important as we deploy AI more broadly. So keep these 3 things in mind. It's really important for people to be able to understand as best as we can, at least the important parts of what are going inside AI. We might not be able to understand everything because these are huge systems, but it's really important for us to be able to understand the important parts and then have control over the parts that we care about from a technical point of view. And then don't forget about the power and the permission, right? That we can work on the technology, right? But we also have to think about how to make these things, how to create the culture and the expectations that people should have, that they can have control over things, and we don't have to just accept AI that's handed down from on high to us. That we should have a high expectation of being able to control these things, and take that power for ourselves. All right, so that's my message for the day and for this community. Thanks very much.
Great, thank you so much, David. You're gonna have to answer questions.
Oh, okay.
So I'm just gonna read you questions, and as long as you can repeat them back for everyone on Zoom.
Okay, great.
Should be good. But first, if there's any questions, I saw a hand earlier, so I don't want to.
I can go last. I have one.
Yeah, go for it. That's okay. You can go.
Oh, I have a little technical question. Why does the vector sum work versus like going along a manifold? If you're on an image manifold, the sum between the two vectors might be better.
Yes. Yes. So I think that okay, so the question is generally about, why do such simple vector manipulations work? The image manifold might be complicated. There might be other operations that would work better. And so first of all, I think that's true that these very linear models, or these linear ways of understanding things are an oversimplification. I think one of the reasons that they don't work 100% is because they are a simplification. What the networks are doing is probably not exactly linear. But on the flip side, there's this funny thing about extremely high dimensional spaces, which is that linear doesn't lack that much power. It's actually doing linear operations in very high dimensional spaces is actually quite powerful and can get pretty surprisingly close to to modeling these nonlinear things. And so we found that this simple linear view can get you pretty far, but I think it's an open area of research. Can you do better than that? Makes sense.
Great.
Other questions?
Question on Slido that says, David, you mentioned changing known bad biases in diffusion models. Do you think it will be possible to detect unknown bad biases somehow as well?
Known bad biases and unknown bad biases. Okay, great. I almost parsed it a different question. Yes. So the question was, we talked about these known biases, like several dozen professions that are all biased, and several thousand artists that we know don't want to be in the data set, and things like that. What about the unknown things? Can we identify and fix unknown things as well? I think that we will. I think it's one of the most exciting areas of research. I think that even before we deal with the unknown bad things inside these networks, there's also an interesting opportunity to even try to understand the unknown good things. And so there's a paper I'd recommend people read. There's a paper by Lisa Schutt. I think she did it when she was an intern for Bean Kim a couple years ago, asking the question, can we extract the unknown human knowledge from a really powerful system that has superhuman capabilities like AlphaZero? Like AlphaZero is better than humans at chess. What does it know about chess that the grandmasters don't know? If it can beat the grandmasters, can we extract new chess strategies out of it? If you have a system that is better than doctors at detecting cancer, can you get some new information about how to read X-rays out of that model that we should put into the textbook that radiologists read? If we have models that can do better things, can we turn that into human knowledge? I think that's so. I recommend reading that paper. It's really an unsolved problem, but there's some really interesting ideas in it, and I think that it's one of the most exciting things to work on.
Awesome. I think we're at time, but maybe you could we're gonna have a 30-minute break in about 45 minutes. So thank you.
All right, I'm gonna switch back to your audio.
Awesome. Ooh.
No.
Yeah, join me again in thanking David for that excellent talk. We are now going to have our first lightning talk session. So every talk is going to be 3 minutes. We'll take 1, maybe 2 questions. So have them ready. And if you're online, please post them in Slido. We're on like a 20-second delay between YouTube. So just post them as soon as you have them. You don't have to wait till the end. I won't read them. So first up, we have Can Large Language Models Explain Their Internal Mechanisms by Nada Hussein, who is not on the Zoom room. That's a different person, I think. Did Nada also say that? In the chat? I don't think
Do you have a video link?
I don't think she gave us her video. Okay, maybe we will just move to the next person and we can sync up with Nada in the break. Our next lightning talk is from Yuzi Ang, who is also not on the Zoom. Okay, so maybe we'll just pop down to Peter's. Is that okay with you, Peter?
Yes, absolutely.
Okay, great. So we're going to start with Explaining Text-to-Command Conversational Models by Peter Stupar.
Thank you. So this explainable is about text-to-command conversational models, as you heard, and we all know that LLMs are showcasing.
If you're sharing your screen, we can't see it.
Oh, sorry.
No worries.
That is. Do you see it now?
Yes, thank you.
All right. So I was saying that we all know. Okay, do you see the screen? Okay, you should be seeing the screen right now. We all know that LLMs are showcasing a decent performance for a lot of tasks, but the lack of understanding these models has limited their use. And explainability of a model is about giving explicit reasons for the model's output, while the interpretability relates to the understanding of the inner model or how it works, basically. And both are very important for improving trust in this kind of technology. For our work, we have fine-tuned several models in order to explore what conversational models can achieve. And one of them is text-to-command that allows users to interact with the internal network APIs using natural language. It is a fine-tuned version of Phi 3 Mini featuring 32 layers. And the model basically takes a question and returns the corresponding list of commands and parameters. So asking our model show the admin state of switch fab3 spine 1 gives a JSON formatted response, and in a very few cases our model gives a wrong command name. And in this example, the part of the command show is predicted correctly, while the part of the command fabric is misprediction, and it should have been switch config, for example. So the classical approach to this is to use feature attributions to quantify the contribution of input tokens to the outputs. And when we look at the mispredicted token fabric here, we can see that the token fab from the switch name is influencing more than the token switch itself. There are other tokens that are labeled as important, which is confusing because individual tokens don't always carry full meanings like the whole words do. And when we look at the words, fabric is mostly influenced by admin, states, and the fab parts. We can also see that the token switch and all the tokens that are related to fab or fabric are negatively influencing each other, possibly due to biases in a training set. So these attribution methods can be sometimes hard to explain, interpret, and they are computationally expensive. So we can try exploring the hidden state, which holds data about the input across layers. So for each of the output tokens, we see the rankings of the tokens possibilities at each layer here. And we highlight the top 5 layers, top 5 tokens at the last layer. And so we see that some, like brackets and quotes, appear as top ranked early on in the layers. Focusing on fabric token again, we see that there is a constant fight between the token fabric and switch for the first rank that ends up with a misprediction. And here, for example, we have a more precise view of the top tokens per layer. We notice some variability initially, but later on, the rankings become more consistent as the model refines its understanding and contextual awareness. The token switch is ranked high here, and this shows that the model converges on it as a strong candidate for the output. Basically, this visualization shows the importance of intermediate layers in elevating certain tokens, showing how different stages of the model contribute to the overall prediction. And on the left, we can see a heat map of the attentions per layer. I'm sorry? Hello? Okay. We can see that the attentions are more focused on the token switch, not focused so much on the token switch, but on the token fab, like compared to the previous layers. And we can see that also focusing attention to the state brings up tokens of state or status. What we can do next is to investigate the last layer of our model and to see a mosaic of neuron activity. So here we decompose the activations into patterns or features that describe the behavior across all neurons. We have a different example now, a different query, which produces multiple commands, and each token is colored according to the feature it belongs to. Some features are primarily active generating structure elements like JSON brackets, quotes, syntactic parts. Other features activate for keys and natural language, which shows specialization in the semantic part. We can click on a specific feature. We can see the neurons that are represented as pie charts showing contribution to each of the features. And some neurons are almost pure here. We can see that means that they fire exclusively upon generation of specific tokens. And on the right, we have a list of tokens and their firings, signatures. We attach attentions, and we can see that similar tokens are generated. And when they're generated, the same neurons fire depending on where the attention goes. So to sum up, we basically believe that the incorrect prediction stems from the model's reliance on the input patterns, in the biases in the training data set, and in the naming convention. So we also saw that neuron activation patterns for subcommands are diverse but overlapping activities. So that suggests that misprediction stems from the ambiguity within neuron groups. And one way to deal with all these errors is to define better training strategy and data augmentation. So finally, I just wanted to thank my colleagues, Gregory, Mermoud, and JP Vasseur, ex-Cisconians, my Cisco colleagues and Cisco itself for work. And of course, thank you for the attention.
Great, thank you, Peter. Awesome. Does anyone have any questions for Peter? Maybe to get us started, I was going to ask, this was a really interesting sort of deep dive into a single particular model mistake. Is this a process that you find generalizable, or how do you sort of use this at scale across these models?
Well, we tried using it on different models. So what we wanted to do is to use the smallest models to see this kind of approach, if it would work with the smallest models. So we tried Phi3, we tried Tiny Llama, and so on. And when it comes to the data, we also tried different models for a bunch of different data sets. And this kind of approach would help us understand what went wrong and how we can adjust the training process to see how to improve the model itself.
Awesome. All right, thank you so much.
Mhm.
Next up, we have TalkToRanker, a conversational interface for ranking-based decision-making by Conor Fitzpatrick.
Hello, can you hear me?
We sure can.
All right, awesome. Just 1 second. Let me share my screen. Okay. All right, can you guys see? All right. Hello. So yeah, my name is Conor Fitzpatrick. I'm a final semester undergraduate researcher at NJIT. This is actually my first ever research conference and research submission to begin with. I've actually only been doing research for 9 months with Dr. Dasgupta. And I also had the privilege of working with a PhD student named June. So yeah, to get started, TalkToRanker is essentially a hybrid visualization and explainable AI model that uses large language models to pretty much power the interface. Our interface kind of has three core modules that power it. So we have the explainable AI augmented input, the LLM augmented analytical input, and the visualization generator. Due to the lack of time, I can't really go into them all in depth, but pretty much each of them work together to allow for the responses that we have to be contextually aware and contextually accurate based on what data set we give it in. And these data sets are pretty much pre-processed with a ranker model applied to them for many different metrics. So to kind of give an example of our interface, we can look at a data set involving emission data. So let's assume we have a scenario involving an admission counselor who wants to maybe find out some information on what, different aspects are best for selecting a candidate. So let's say this admissions counselor has no concept of data science at all, does not really understand what many concepts mean. So maybe it'll start to ask questions that are a bit more in line with the average person. So let's start out with maybe it'll asking what is the most important factors when admitting a student. So the admissions officer will ask this, and they'll be given some information based on feature attributions such as the GPA score, TOEFL, GRE. Now maybe they want to see how much of an influence these factors have. So they're going to ask, what influence does GPA and TOEFL have on admittance? So as you see here, there was a little bit of an error, but that's okay. So they may ask now for more of a focused in data science question. So what is the correlation of CGPA on admittance? So yeah, now here they're given a scatter plot showing the correlation compared to the ranks and value of GPA. So as you can see here, we're given the ranks as a bar plot, and we can see that there is indeed as GPA scores get higher, we can see higher ranks, and as GPAs get lower, you can see lower ranks and a lower chance of admission. So with this increase, we now maybe want to select some information. We can do a lasso select, but we also can ask for the top K. So maybe we can ask to select, let's say the top, 200. So they can select the top 200, but maybe they also want to get a bit more of a narrowed in perspective on the distribution. So they can actually ask maybe how the data is spread out for the GPA. So they can ask, how are the GPA scores spread out? And they're given a distribution here. So maybe they now want to also ask about what a different selection looks like, but they also want to keep this one in mind. So they can track this response. Let's say they're from my college at NJIT. So they track the responses at NJIT. And what this allows them to do is it allows them to compare different states. So if they select, let's say, a higher group, like the top 400, they can actually compare the different states. So yeah, show me track response, and they have the ability to play an animation showing the old and new selection. They also have the ability to see the stability of the data to see how stable the ranker is in their selection. So they can ask to see the stability. Yeah, and as you can see here, there's different levels of stability of the ranker at different areas. And again, they can also apply selections here that are correspondent to the rest of visualizations. Finally, if they would just want to see the raw data, they can ask to see it as a table. And here it is. Yeah, that's pretty much it. Yeah. Any questions? Sorry if I was a little bit nervous my first presentation.
That was great. Thank you so much, Conor. And
Thank you.
congrats on your first presentation. It was excellent.
Thank you. Thank you.
Let's see. Do we have any questions in the audience? Yeah.
I have one, and actually it's probably a question for everybody.
Okay.
If I look at the website, it says that you're targeting the average person, and in the talk before, there is this idea of a human. But also in David's presentation, he says about human understanding. Who's the human that we are talking about here?
Yeah, that's a
certainly not the average person. So I think clarifying that, what is the human that we have in mind, and you may help us, evaluating what we are looking at.
Yeah, that's a great question. The question is, who are the people that you're envisioning are using this, or the people that you're designing for?
So ideally, the goal of this interface is for it to work with both people who have, there's a term I kind of like use a lot when developing it, data literacy. So people who know what terms like, stuff from data science and statistics, like standard deviation, correlation, people who can ask those questions, we want them to use it, but we also want people who may not know what those terms are to be able to use it. Unfortunately, we did have, this is the first time it actually acted up. Kind of unlucky, but for example, one of the things we did a lot when testing was using a lot of questions that weren't using explicit terms like correlation and all these other things. And under the hood, pretty much what we try to do is we actually have tasks that match up with those things. So as someone who isn't a data scientist, right, you may want to, for example, the one example we did give was they're asking how much of an influence does GPA or TOEFL score have on admittance? To a data scientist, one thing that you'd be looking for is correlation, but if you're an admissions counselor at a college, you may not necessarily know what that term is. So what our end goal is to allow for this interface to be able to kind of handle questions that are for both people with that level of expertise. So if they ask that question, it should handle it no problem. But we also want there to be more abstract questions that are not necessarily related, but we kind of want to work towards, and this is one of the areas of future growth we have for the interface, is to kind of enable understanding less data sciencey questions, if that makes sense.
Yeah, that makes a lot of sense. All right, thank you again, Conor. That was excellent.
Thank you.
And if questions come up at any time, just hop over to the Discord. All of our presenters are on there too, so they can answer anything that you're interested in. Okay, Conor, if you could just stop sharing your screen. Next up, we have Explainability Perspectives on a Vision Transformer from Global Architecture to Single Neuron by Anne Marx and Diego Arapovic.
Hello, everyone. Just sharing my screen. Is it visible?
Yes.
Okay, so greetings from Zurich. My name is Anne Marx. I'm a graduate computer science student at ETH, and I'll present our blog post with the title you just named. So to our motivation, there are many papers that present XAI methods for vision transformers. However, after some research, only few offer the readers the option to really interactively explore a model on their own, or some interactive blog posts only tackle one or two XAI methods, which is why we created this educational blog post that investigates the vision transformer image classifier, which was trained on ImageNet. We have the following 3 goals. So firstly, we want to enable the user to learn about the VIT through self-exploration of several XAI methods. And in that regard, the blog post format makes it quite easy to guide the user with complementing text. And it also makes it possible to inform and warn the user on limitations, as not every method might be truthful to the model behavior. And furthermore, we also allow for a comparison of different methods. So in total, we have 6 small explainables in the blog post, which are divided into 3 complementary main parts. So first of all, we start with a rough explanation of the vision transformer architecture, and then we divide the blog post into model externals and model internals. So for us, model externals focuses on the model input and output. So we investigate the model as a whole and select a few input images for exploration through gradient-based methods and an occlusion method. And then secondly, the chapter model internals kind of focuses on investigating the modular parts of the network, namely single neurons and attention heads, for example, through activation maximization. Due to limited time, I'm just selecting 2 small sneak peeks of the blog post. So first of all, this explainable is kind of a checkpoint for the user to test this mental model throughout the blog post. So he can occlude certain features of an image and then forward it to the VIT classification network to see how the predicted class probabilities change. So assume the user has built a mental model through previous gradient-based methods in the blog post. For example, that the strings of a harp are crucial for the classification. And now in this method, he can kind of test the robustness of the network and also test his mental model on whether the strings on the image are really, really crucial for the classification or whether the network just focuses on them primarily. So this kind of tells the user or kind of helps him to better understand what the VISxAI methods really tells about the model. And lastly, one of our other main contribution is to introduce a new adaptation of the activation maximization method, where we basically take the optimization goal and apply it to all attention scores of each attention head. And we call this method attention score maximization. And here in the results, we can see kind of similar to activation maximization that the complexity increases with network depth. However, we also acknowledge that much further research should be done to fully understand the implication of this method. So that was all from my side, just to stick to the 3-minute format. Thanks for listening, and I also want to take a minute to thank my co-authors and also my supervisors listed here. And if you would like to have a chat, I would be really happy to talk more about VISxAI via the channels. Thank you.
Great, thank you, Anne. Any questions for Anne? Yes.
I try to speak out, hopefully it transfers to the microphone. For the occlusion tool, have you thought of also showing the heat maps that you produced from the VISxAI methods on top of the image so that you have a better clue of where to start occluding things?
Okay, the question was, were you able to hear that?
Partially, could you just summarize it again?
Yeah, I'll repeat it. So the question was, for your occlusion visualization, have you thought about visualizing the heat maps over top so that people sort of know where to maybe start occluding or what hypotheses they might want to test?
Yeah, that's actually a good suggestion. Maybe we'll add that in the future. So no, we haven't thought about that yet. Good input. Thank you. But like the user can also kind of scroll upwards, see the heat map, and it's quite close to each other. So hopefully the user can kind of remember for the time of scrolling which features he should include. Yeah.
Awesome. Very cool. Well, thank you so much, Anne. If there's any other questions, feel free to hop into the Discord and ask them there. Next up, we're going to have Where is the Information in Data by Kieran Murphy.
All right. Is that working?
Yep, looks great.
Cool. All right. So thank you for having me. These have been really fun to watch. My name is Kieran Murphy. I'm a postdoc at UPenn working with Danny Bassett. And I want to tell you about this explorable that we made earlier this year. But it's kind of neat. Just a quick little shout out. So I've never done this sort of thing before. And I really just hollowed out a post by Adam Pierce. So I'm excited for your talk later. But yeah, this is straight from like the grokking explorable. But yeah, so I kind of just want to walk through some of the experiences I had making it. The point of this is it's based on a recent interpretability method we've been working on, where instead of trying to understand how a neural network transforms data, focus instead on what information it uses. And since it's kind of a weird idea to localize information, the explorable is meant to build intuition. So we work through several examples that build in complexity, and they're all based on communication. So the first one is this telegraph line where you're trying to send one of two messages, and there's noise that you can vary with a slider. And I think this was one of the recurring themes. It was just very satisfying to take a three-dimensional plot and move one of the dimensions to a slider bar, in contrast to, say, animating the third dimension. So that was really fun. But then where it really took off is leveraging the freedom even more. So then the next example is you have two telegraph lines, and you're concerned with the space of all compression schemes of messages down those lines. So here, every dot is a compression scheme. But what you can do is then mess with the data distribution. So now, rather than just a three-dimensional plot, there's really this kind of four-dimensional space of two-dimensional plots, and everything's just calculated on the fly. So it feels just like you're throwing the user into this much bigger space of figures. And then that gets amped up even more. So this next one took me the longest. But now there's still two telegraph lines. There's more messages that you could send. And you can again vary the data distribution. So up top, you can toggle these message spaces. You can click these little buttons. And then you train some networks in your browser that compress the information and find optimal schemes. And now you still have a slider bar where you can watch how the optimized latent spaces change, how the information changes. It feels like this is a playground where whether you're a novice or you're an expert in information theory, you can just go to town exploring this much bigger space on your terms. So there's that. And then it all kind of builds up to a real use case, still kind of a toy, but this is the classic bike share data set where you're trying to regress how many bikes were rented from 12 features. And so now, rather than trying to restrict function complexity, we just want to know where's the information coming from before it goes into a black box machine learning model. And so there's, again, a slider that sort of takes a third dimensions role. But what was really fun here is guiding focus. So there's a lot going on. There's a curve per feature that corresponds to a matrix down below where you can see what information is actually being used. And so anyway, I just found that this experience made me look at making figures in a new light. So anyway, I appreciate the time. Thank you for having me here. And if there's any questions, happy to answer them.
Awesome. Thank you so much, Kieran. Do we have any questions for Kieran? I have one. So this is a really cool method to think about where the information is in your data. How do you think about maybe using a technique like this alongside another interpretability technique?
Yeah, it's a great idea. I think that there's there's just a lot you can do. And so then mixing and matching. Right now, this is intended to leave the machine learning model untouched. But then it's a great idea to try to throw some interpretability in there and have some interpretability on what information is being used on the input side. Yeah, I like that. I'll jot that down.
Awesome. Well, thank you so much again. Nada has sent us her video, so I will screen share that. And so next up, we will have Can Large Language Models Explain Their Internal Mechanisms by Nada Hussain.
Hi, I'm Nada, and
Sorry. This one? Thank you, Helen. Okie dokie.
Hi, I'm Nada, and I work on Google's People and AI research team, where as part of our work, we publish visual interactive explorables on the latest AI research. This submission is our latest explorable. Can large language models explain their internal mechanisms? This is a visual exploration of patch scopes, a family of interpretability methods that leverage an inspection prompt to understand hidden representations in LLMs. First, we cover the patching operation with a scrollytelling walkthrough. We take an initial source prompt, say United Kingdom, and run it through a source model. We can then extract a hidden representation of interest at any token position and layer. We construct an inspection prompt that is designed to extract specific information about our representation. Here we use the largest city in X. At a specified target location, we patch the hidden representation from the source model into the placeholder X token and continue generation. If we've chosen a good inspection prompt and suitable source and target locations, we see the target model generate an output that gives us information about the hidden representation. Here, the target model successfully outputs London, the largest city in the UK. We move on to our first experiment, where we use a few-shot entity description inspection prompt to understand the entity resolution process of a model. We provide many example entities as source prompts and visualize the target model's output at each source layer, as well as an evaluation score of the accuracy of the description, allowing users to see the pattern of LLM sequentially processing tokens in reverse order. We see here with Diana, Princess of Wales, that the output first describes Wales, then shifts to describing the title Princess of Wales before finally resolving the entire subject. We then compare patch scopes to probing for attribute extraction. We provide a list of reasoning tasks where users can visualize the performance of each method across examples and select from representative examples at each layer to see the written outputs from both patching and probing. For example, we see patching performs well on the country currency reasoning task, but it performs a bit worse on the object superclass task. Overall, we find that patching outperforms probing in early layers on 7 of 8 tasks, suggesting that it's a viable alternative to probing that comes with the advantage of needing no training data and providing a flexible, simple process to easily extract the desired attribute. Finally, we take patch scopes a step further to try to correct model behavior in a few multi-hop reasoning examples. Using the same source and target prompt, we can patch information from one reasoning query into the other, effectively splicing the model's own intermediate answer to correct its response. We provide users with this dashboard, allowing them to select queries and navigate through a grid of source and target layer pairs to explore combinations that correct model behavior, as well as expose failure modes that we might want to explore about patching in the future. Thank you.
Awesome. Thanks so much to Nada. She is having internet issues, so she won't be online in our Zoom channel, but she will be online in Discord if anyone has any questions. So that wraps up our first session, our first lightning talk session. We will be back here at 10:15. So enjoy a break, take a coffee, hop in Discord if you have anything else to chat about. See you then. Back, everybody. We are starting our next session with our next session of lightning talks. And first up, we have The Illustrated AlphaFold by Alana Simon and Jake Silberg.
Hi, We are Jake and Alana, and we wrote a blog post. Oh, wait, I should share my screen. Okay, cool. We are Jake and Alana, and we wrote a blog post called The Illustrated AlphaFold, inspired by Jay Almar's iconic illustrated transformer. We walk through basically all the implementation details of AlphaFold 3 using visualizations to try to make the architecture as easy as possible to understand.
So as you likely heard about this week with the Nobel Prize, AlphaFold 2 is a machine learning model that predicts the structure of proteins from their sequence and has had a profound impact on structural biology and protein design. AlphaFold 2 also introduced multiple architectural innovations that are now standard in modeling protein structure and sequence. This year, DeepMind released AlphaFold 3, which is more flexible. It can predict the structure of proteins and can also predict the structure of protein complexes with other proteins, DNA, RNA, and small molecules. And while this change for AlphaFold 3 makes it really exciting for drug discovery, it also makes the model a bit more complicated to try to understand all of the details. So AlphaFold 2 and 3, the papers contain over 100 pages of supplementary materials, including extensive pseudocode and complicated algorithms, which can be intimidating to work through and challenging to see how all of the pieces fit together.
So as a visual learner that we, and probably most of you are, we really wanted to see how the information flows through the model to create this final prediction. So we made diagrams for every tensor, every matmul, and just use those to follow how the many input sources get transformed through the model using specific colors and patterns in the diagrams and the text to just keep track of everything. And then in trying to understand the model ourselves for fun, we basically made the explainer we wished we could have read. So we then wrote it up, made it pretty, and shared it for other people trying to parse through the dozens of algorithms in the paper. In the post, we go through quite in depth some of the well-known innovations from AlphaFold, like triangle attention, triangle updates, some of the other custom attentions, and then also discuss some of the newer additions added for AlphaFold 3, like the structure diffusion module. And we break the model down into 3 main sections, we describe it. There's input preparation, in which there's a bunch of retrieval, tokenization, some kind of bioinformatics, representation learning, where most of the compute happens, and then structure prediction, along with the many loss functions and other training details. And as both the original paper and our blog post are quite long, we wanted to make it easier to find your way around and not get lost. So we made this kind of interactive table of contents where it's a high-level overview of the architecture. You can hover over any part, click it, and it will take you to the part of the blog post that describes that section of the model. And then as you go along, if at any point you get kind of lost, as you might, there's a lot going on, you can just check back in with this diagram, see where you are, figure out what that section is, what it's focusing on. And then once we added this, we realized I kind of just wish other models always came with some interactive way to read it like this. So yeah, with that, we just want to say thanks. We love learning via these high effort visual explainers. So it was very fun to make one ourselves, and hopefully people find this useful. And yeah, it's cool to have this shared with the other awesome papers in the workshop.
Awesome. Thank you so much, Alana and Jake. Yes, we have a question. A live question. So.
Hi, Hendrik here. Amazing work. I'm glad you took this task on because I think it's very, very complicated to actually try to do some kind of explainability for this weird model. Do you got an intuition while working with it about how much functions actually derived from all the pre-processing and post-processing versus the actual machine learning model? So how much kind of workload does the machine learning model do versus the ingenuity of encoding the data to actually work with this kind of model?
Do you want to take a Jaker?
Yeah, I can take a first stab and then let me know if you have more to add. I think in terms of pre-processing, our understanding is really a lot of work did go. So the model is trained on the protein database, the PDB, but our understanding is there was a lot of data engineering that happened to kind of clean up the PDB and sort of make it more useful and consistent for the model. So I do think pre-processing played a role. And then also it still uses the multiple structure alignment, which basically, matching sequences to similar sequences in the database. And that retrieval process also does seem to really boost performance. And basically the closer the match in the MSA module, the better the structural prediction is able to do overall. So I do think pre-processing continues to play a pretty big role. But given that, that those parts are kind of similar across the AlphaFolds, the machine learning part does seem to be getting kind of better and better. A lot of maybe you have more to add.
No, I totally agree with that. The one other thing I'd add is that it seems to be quite protein dependent. Like there's some protein families where you don't necessarily need as much, or like don't benefit as much from all of the pre-processing or having like a really robust multiple sequence alignment, whereas for others it's much more important. And that depends a bit on like what other training data is available and also like the structure of the protein family itself. But yeah, definitely like this is an architecture in which a lot of the algorithmic additions were really critical. And you see that like after AlphaFold 2 came out, a lot of these like custom attentions we walk through started like sneaking their way into lots of other machine learning models that work on protein spaces, or like proteins and small molecules. And that has been helpful. Not all of the pieces were necessary. Some could be kind of bladed out, but a lot of them have been actually quite critical.
Awesome. Thank you both so much. Next up, we are going to have a visual tour of empirical neural network robustness by Chen Chen.
Okay, cool. Can you see my slides?
Yes, we can.
Cool. Hello, everyone. I'm Chen from University of Maryland, and I'm happy to be here presenting our interactive article, A Visual Tool to Empirical Neural Network Robustness. So modern image classification models for recognizing objects in images are mostly built with convolutional neural networks because of its high accuracy. However, researchers have found that with very slight changes to the input image, the model can be misled to give wrong predictions. So to defend, people have been proposing training mechanisms to avoid such behaviors of models, leading to the rise of machine learning robustness research. In this project, we develop interactive visualizations to convey key concepts and insights along this line of research, conveying the knowledge to broader audiences. So the first insight we show is the power of CNN on image classification, where we use a line chart to show the training process and a rating bar chart to show the output distribution. As you can see here, the accuracy is raised to above 90% at the end. However, we can also observe some potential instability. For example, in the late stage of the training, the prediction still jumps between frog and cat for this cat image. So based on such observations, researchers have found ways to attack a model, adding noises that are imperceptible to the input image. A famous attack method is called projected gradient descent method, as shown in this figure. It perturbs an image in the direction that hurt the prediction the most through the gradient descent method. So PGD attack turns out to be very effective. Like on this cat image, after only one step, the prediction is folded into frog, and the later steps continue to enhance this misclassification. However, to us human beings, the differences between steps are hard to see. Looking at the whole data set, it is clear that initially, the model has a very high rate of correct predictions, while only after one step, the correctness reduced by large. We can also observe diverse behaviors on different classes, like dogs are more perturbing to cats, while cats are more into deers. This raises more questions to the decision boundaries of CNNs on images. So how can we avoid this? Well, later researchers have correspondingly proposed defense mechanisms called adversarial training. The idea is pretty simple, just using PGD attacked images instead of killing images during the training phase. And that simple idea is indeed effective. Here is two bump charts to show the predictions of two models on the cat image on the 5 steps of PGD attack. As you can see here, the regularly trained model's confidence on the image being a cat greatly reduces after just one step, while the other one, a adversarially trained model, although becomes less confident, still outputs the correct label. But there's no free lunch. The adversarial training comes at the cost so-called accuracy robustness trade-off. As shown here, adversarial training produces models that are less accurate on clean images. As this epsilon, which is a magnitude of attacks, gets smaller, the produced model gets closer to the regularly trained model. Gluing all the insight together, we introduce our full article. We have an additional image panel on the left side of the screen displaying around 500 images from the CIFAR10 dataset, and the image selection is synced with the whole article so that you can explore the model's behavior on individual images. With that, I would like to thank my co-authors, and I'm happy to take any questions.
Awesome. Thank you so much, Chen. So,
I'm curious about what the direction of the gradient descent is with respect to the decision boundary. Is it something that the author saw or like that?
Yeah, the question is, What is the direction of the gradient descent with respect to the decision boundary?
So when you're performing the attack, it's basically shifting you away from the correct prediction. So for example, if you're a cat, then you are close to a deer category, then the attack will move the image more close to the deer's category. So it's more towards the decision boundary, but it's on the opposite way. So it's just trying to fool the model and trying to get an image that it still looks the same, but it moves the prediction more onto other categories.
Awesome. Thank you so much. I see there are a couple more questions in the Slido, so maybe I think our student volunteer is going to move those over to Discord if you want to answer them there.
Cool. Thank you.
Great. Next up, we have Panda or Gibbon, A Beginner's Introduction to Adversarial Attacks by UZU.
Sounds good. Just give me 1 second to share my screen.
Absolutely.
Okay. Hello, everyone. My name is Yushay. I'm a PhD student at the University of Waterloo, supervised by Dr. Zhen Zhao. And today, I'm here to present our interactive explainable titled Panda or Gibbon, A Beginner's Introduction to Adversarial Attacks. So what exactly are adversarial attacks? These are attacks that specifically target machine learning models by applying a thin layer of noise to input data, like images, to fool models into making mistakes. Here, we're looking at the very first adversarial attack called the FGSM attack. On the right here, I have 100 floating data points, each representing a sample image from the CFAR10 dataset. For each data point, we divide them into two halves. The left half represents the label, while the right half represents the model's current prediction. And here, we're going to try to explore ResNet 34 model's behavior under the FGSM attack. But first of all, I'm going to actually rearrange the data points a little bit by applying this method called TSNE, a dimensionality reduction method, so the spatiality of these points represents how ResNet perceives these images. Additionally, we added a layer of hexagons in the background to visualize the global distribution of the entire dataset with 10,000 images. Next, let's try conducting the attack on this model. As I increase the perturbation size here, we apply more and more noise to the images, and you will notice that the model's accuracy starts decreasing all the way from 93% down to 57%. The images are moving around rapidly in the feature representing space with more and more color changes, telling us that the model is making more mistakes. Additionally, we can see the before and after images, and you will notice that the more perturbation size we apply, the more obvious the noise is. So attackers tend to want to find this middle ground where the perturbation is just enough to cause a misclassification, but not too obvious to the model user. Next, we're going to look at a different ResNet model. We're going to call this model ResNet Star. This model has the same architecture, but trained with adversarial training, a common defense against these attacks. Let's try the slider again. This time, you will notice that there's barely any changes in the distribution at all, indicating that this model is much more robust. But why is that? As we click on some data points, we can see the gradient visualization between the two models on the same image. And what you will notice is that compared to ResNet's gradient visualization, ResNet Star's gradient visualization actually has lines and shapes that resemble the original image, indicating that it relies on more human interpretable features for classification, leading to improved robustness. That is the end of my presentation, and I am happy to answer any questions.
Awesome. Thank you, Yuji. Do we have any questions for Yuji? Yeah, we have a question in the Slido that says, love the design of the article. Meta/authoring question. How did you decide what info to put in the optional expandable boxes?
Oh, okay. So for the buttons on the website, it's mostly more mathematical concepts and more, I guess, just technical concepts of the attacks. Because since we designed this tool mostly for non-experts, and in our case, we define non-experts as those with computer science background, but don't or a little bit of machine learning background, but don't exactly know adversarial machine learning. So we want to at least provide an overview, like an intuitive approach to the general concepts.
And when you click these buttons, actually, let me just give like a quick demonstration. Yeah, so when you click, for example, show technical details, it will just show you like the actual equation and details of the technical approach behind the attack we're visualizing here. Hope that answers that.
Yeah, that's awesome. All right, thank you again.
Thank you.
Next up, we're going to have What Can a Node Learn from Its Neighbors in Graph Neural Networks, presented by Harry Liu.
Can we see my screen?
Yes, we can.
Hi, everyone. I'm Harry, and I'm a second-year undergrad in computer science. Our talk is What Can a Node Learn from Its Neighbors in Graph Neural Networks? This work done in collaborations with Chongwei Chen and Matthew Xu, supervised by Professor Qianwen Wang at the University of Minnesota. First, what is a graph neural network? Graph neural network is a type of neural network for processing data that can be represented as graphs. Some examples include community detections in a social network, protein classifications and generations, product recommendations in a recommender system. Due to the huge success of graph neural network, we expect there's a large demand for GN educations. However, due to the complex computational mechanisms of GNNs, it's often difficult for deep learning novices to learn about GNNs. From the existing work, we found most current GN educational resources mainly focus on high-level concepts, often failing to present the detailed inner workings of graph neural networks. And the current GN interactive visualizations mainly focus on specific aspects of GNs, such as performance and evaluations. Therefore, we introduced GN101, the first interactive visualization tool for learning GNNs. And here we will have demonstrations for our systems. So first, like you can select different input data, and then we can also select the different tasks and models. Due to the time constraint, I will use the GCM models and the graph classification task for these demonstrations. First, you can click the click to predict buttons, and the system will visualize the model structures. And you can also switch between the JSON matrix view and the node link diagram views. And by hover-overs node, you can see the inputs and output of a specific graph convolutional operations. And by clicking on that, it will visualize the message passing operations. And by hover-overs certain components, it will visualize the detailed mathematical operations. And by clicking on the matrix multiplications, it will show up animations to indicate the matrix multiplications. And by hover over different components in the mathematical formulas, it will also highlighting the components in the visualizations panels. And I think that's all. And thank you for having me here. And I'm happy to answer any questions.
Great. Thank you so much, Harry. Do we have any questions for Harry? Yeah.
So this is a really cool tool. So it's mainly showing like homogeneous graphs. I was wondering if developers thought about like how would they represent like heterogeneous graphs for this like one-on-one function.
Yeah. So the question was that this is a really cool tool, and it seems like it focuses most on homogeneous graphs. how would you sort of think about using this tool for heterogeneous graphs?
I'm sorry.
The question was that the tool seems to work on homogeneous graphs, and if you had thought about extending it perchance to heterogeneous graphs.
Yeah, I think so. Currently, we are more focusing on the homogeneous graph, and I think like in the future development, we can extend this to that kind of graph.
Awesome. Thank you so much, Harry. Okay. Okay. Next up, we're going to go to inside an interpretable by design machine learning model, enabling RNA splicing rational design. And that's going to be presented by Matthias Aragao.
Can you give me 1 second? I share my screen. Okay. Good morning, everyone. My name is Matheus Aragão, and with this explainable, we will explore the question, how can we visualize the decision-making process taken by a machine learning model? This is how most ML researchers show a network with a modular format, but I will demonstrate how interactive visualization allow us to open the machine learning black box. We use as a subject of this study an interpretable by design machine learning model for RNA splicing prediction. And with this, we want to interpret how a given exon leads to a given PSI prediction. In this model, we interpret two outcomes, exon inclusion and skipping. Inclusion refers when a given exon is included in the splicing product, and skipping when the exon is excluded from the splicing product. The ML model uses an experimental metric called percentage splicing, or PSI, as the ground truth during the training of the network. And the PSI is a ratio of exon spliced in. We are able to represent every convolutional feature with what we call a feature motive. These feature motives were learned during the training process, and we represent the inclusion features with a blue background and the skipping with, I'll play it again, sorry. And the skipping features with a red background. Yeah. There are several features, and we can map these features along the exon, which allow us to observe the regions in the exon that have been activated the most by a given feature. The height of the bars represented the strength of that particular feature in that specific area of the exon. And here's the example of an inclusion feature. And here's the example of a skipping feature mapping along the exon. The resulting stacking of all these heights at a nucleotide resolution allows us to plot what we call the exon view. With the exon view, researchers can explore the areas of most interest and zoom into the nucleotide level to explore the features contributing to the height of that particular position. For example, oh, you cannot see my cursor. By summing all these individual strength units, we get a total strength for the inclusion and skipping class. The model takes the difference between these two class strengths to get the PSI prediction. Examining the following study case, our visualization aids researchers in understanding how mutations can impact splicing outcomes by visualizing the change in inclusion and skipping strengths. The following exon has an inclusion ratio of 0.15, which characterizes it as a skipping candidate. But now if I change in the position 31, from going from a C to an A, we can observe that the bottom half of the graph that previously in the red area, now symbolized by a much lighter area, as you can see, used to be larger than the current darker red area. Now, if that mutation there is reduced throughout several nucleotides, and that drastic change on the skipping section of the graph explains the new inclusion ratio of 0.91. This visualization immediately shows researchers how a single mutation can significantly alter splicing predictions. So just to conclude, an interpret by design ML model coupled with some interactive visualization makes complex splicing predictions explainable and allows researchers to interpret the splicing outcomes of predictions. Thanks so much, and that's our presentation.
Awesome, thank you, Mateus.
I'll stop sharing, and if there is any questions, I can also share the original link. Yeah.
Hi, Hendrik here.
Hello.
One question is, have you also tried to look into the isoforms and try to kind of predict the probability for a certain isoform given the specific gene? Or is it all like global measures, essentially, how robust this kind of gene is in being spliced in or spliced out? I mean, splicing in is not a thing, but spliced out or not? Or would it be helpful to kind of align it with the isoforms?
So the model, which was developed previously by some members of the team, did not take like genomic data. So it was built for the train, as I mentioned before, the features, those specific features, right? Let me just, those specific features, they were learned during the training process, and they came from basically learning specific things from this synthetic data set of 300,070 nucleotide long sequences, right? So I don't know if I understand your question, but you're saying basically if this can, how can I say, generalize to other isoforms, right? So I think that would depend on the training set.
Yeah.
Yeah, and the interpretability comes, the members of the team are working like, let's say a next version of the model that was built but to be interpretable, and taking consideration other models in the in the research area called, for example, Pangolin or VISxAI. They already consider genomic data, and which can greatly improve the interpretability part with their capacity to interpret longer sequences can definitely improve the results and probably generalize for the isoform. Yeah.
Okay. Thank you very much.
No worries. You're welcome.
Great. Thank you, Mateus, and thank you to all of our lightning talk presenters in this session and the previous one. That wraps up all of our lightning talks for today. So next up, we're going to have Adam Pierce give our closing keynote, asking why aren't we using visualizations to interact with AI? Adam has been a data visualization practitioner for over a decade, spending time in newsrooms at Bloomberg and the New York Times before taking his skills and applying them to AI explainability at Google Pair and now at Anthropic. He consistently creates such high-quality visualizations that seem to somewhat effortlessly explain these really complex ML concepts, and we are also proud to have him as a VISxAI alum. So please join me in welcoming Adam.
Thanks, Angie. Let me share my screen and I'll start. Okay. Yeah, so I got into machine learning and machine learning visualizations just about 6 years ago now. And it seemed like such a natural fit when I started, right? We have these like super complicated, high dimensional things that we can't just understand. They're doing magical things. And we have visualization, on the other hand, which is the fastest way of getting information into our brains to our visual cortex. So let's just mash them together and this will be magical and we'll be able to unlock why these things work. But instead it's, 2014, and this is like how we interact with the models, which is great. But we're sort of going through this like very narrow straw of like text and tokens back and forth to the model, and not really using all these other HCI tools we have. And that's how we interact with the models as users. And then as like people working to understand models, we communicate like this. In a PDF, there's a bunch of equations and maybe a couple of static charts, but again, not using this high bandwidth interactivity. And to get at why, I want to rewind another 6 years and maybe get up on a little bit of a soapbox since I've been invited to. And so zooming back to 2012, it also seemed like interactive visualization was transforming another field, news graphics. Every couple of weeks, the Times would put out a like new visualization that like totally changed how I looked at data, and you could interact with them. And it seemed like we were like living in this complicated society that was becoming increasingly incomprehensible, and interactive visualization was going to be the way we're going to like democratize people's understanding and be able to make informed decisions about what they were living in. But we go forward again to 2024, and I have a lot of friends still making good work in newsrooms, so I don't want to make these takes too hot. But I sort of feel in my bones we haven't made anything as good as like this 512s pass to the White House in the last decade. And so why? And to answer that, I'm going to start with like why things were going so well like a decade ago in newsrooms, and then sort of talk about why I think that sort of ended. So one thing is that just like there's this new fast distribution platform. We had the web had been around for a while, but Chrome and V8 start to get like very fast between like 2008 and 2013, like literally 4 times as fast, which makes it possible to load large data sets in the browser and then like start doing things with them interactively. And then on top of that, there's this like there's a sort of capacity overhang from like visualization research going back a long time. So people publish all these papers about how to like, nicely lay out a tree, but it's locked in the paper. You have to like go read this paper and like parse this code and write it. And Bostock kind of like unlocks a lot of this with T3 by making this like amazing toolbox filled with like all these treasures from visualization research over the past 50 years, and makes it so that you can just like drop it in your page and then have this like beautiful tree diagram thing happening. And another sort of like thing in the mix there was also just like this rich history. Just beyond just like making the toolbox, also published like over 1,000 examples that make it very easy for people to like remix them and combine them and do new things with them. And then all this is also taking place in a newsroom, which has another history of like graphic design and information encoding. And if you can just like stick tooltips and sliders on these things that people were making, have been making for like literally the last 100 years, they become better and new in ways people didn't anticipate. And I think like that's just not me being like newsrooms are great. Like empirically, a lot of like front end frameworks have come from like newsrooms of like Drupal, Underscore, Backbone, Svelte. You have to like have these clarifying deadlines that force you to get stuff out the door and make it good. And then that sort of feeds back in the framework and makes it better. And it's a nice cycle to have going. The other thing that deadlines give you is the ability to default on technical debt. So you publish a story and you're done with it and you move on to the next thing, which in the 2010s let us do these kind of, I don't want to say like, they were essentially like a lot of like very gratuitous animations. And we could ship these because we could experiment and throw away the code. And it was like, if you picture like using a computer, I think our like modal reader a decade ago was like someone bored in the office and like kind of clicking around, and these like flashy animations were like much more visually appealing than a lot of else was on the internet. And so it was like we were sort of hacking the sort of nascent attention economy a little bit, and putting a little bit of sugar on top of like this like data that would help you live your life and be useful and good. And this sort of like stops working once the like giant platforms realize that people do like a little bit of sugar and interactivity on their sites, and instead of just having like some sugar sprinkled on your vegetables of data, you can just like have like hyper optimized sugar there's more than you can like consume in your waking hours, and it's like tailored specifically for you. And you can't really win against that with news graphics. So I think the like air starts to go out of the balloon a little bit. Another like trend sort of pressing against like you have these like rich, like carefully annotated, perfectly laid out pages that guide you through understanding things. And when we switch to mobile, you can't do that anymore, and everything's forced to be in a little rectangle and it's responsive. So you're stuck just like making a bar chart. And another thing, like as we start tracking things, this is like a ongoing debate in the community, which I'm just gonna like throw out again. You track things and it turns out that like nobody clicks, or a fraction of people who view the article actually like meaningfully interact with it. So you like multiply that by like the small number of people using desktop, and then the small number of people actually click on it, and it's like no longer worth making these it's harder to justify making these interactive graphics. Some more subtle issues that I think have sort of the news graphic space sort of started bumping again is Bostock also gave this nice talk about how like design is a search problem, and you sort of like branch out a lot and explore a bunch of ideas, and you like find something good, and that's the like graphic you ship at the end after you like refine it a little bit. And I think a lot of the low-hanging fruit has been sort of picked, so it's like harder to justify spending a bunch of time doing exploratory interactive research in a newsroom, or like trying new ideas in a newsroom. Like the first time you make a like cumulative home run record chart, it's like, wow, you can like pivot this data and look at it in a different way, and this is amazing. And then the next time someone breaks a sports record, you're like, well, I'm not going to spend a month looking at this because I already have a good form. And then so you make that form, and then you make it again, and then you make it again, and then eventually flowing data makes fun of you. As required by law, when it comes to sports records over time, you have to make a cumulative stats chart. And that means it's not as new, it's not as fresh, it's not as vibrant. And part of me is like, is this all just like nostalgia? Like I can only fall in love with like graphics for the first time once. And, but I do think there's like a certain quality to things that are being done for the first time. Like Tron is like the feature film with computer graphics first time. And it has like Ken Perlin is like working on the project. And you get this like influx of people who are excited by the possibility and come in, and then as things sort of like peter out and the like lines have been drawn in, people leave. And at least in news graphics, that looks like Netflix hiring away everybody that's like really interested in this like interactive stuff to go do mysterious things at Netflix. And the people who are interested in like more like news for news, well, they have a great library of like charting techniques and data wrapper, and can kind of focus on that in a more fluent, easy way. But the interactivity of the bit is sort of like no longer a key central thing, and it's like the thing I was most excited about. So yeah, as I was saying at the start of this, 6 years ago, I got into machine learning visualization, and that's largely for like similar reasons as I got into the news stuff. Is I was just like, wow, look at all this cool interactive stuff going on, and I'm really able to like, these visualizations are showing me like new things and new ways that I haven't thought before, and I really want to make them. So just, I mean, I'm sure everyone's sort of familiar with this like canon of work, and it seemed like a lot of the pressures that were like affecting like news graphics would be like less important if I like went and did new stuff in machine learning. So I went over to Pear at Google to do that. And I started this series of interactive AI explorable articles. And I was sort of like laid out sort of like, it was like unclear what these were for or why we were making them. So I kind of made 3 rules for myself at the beginning of that we would show new machine learning research. We're in Google Brain and had like access to all this new stuff, and machine learning's increasingly important, so we should educate people how to use it. 2, we should like try to make them like understandable to everyone landing on the page, and like maybe not everybody, as like Google defines like billions of people using like Google Maps, but like I just had like an Imagine Times reader in my head as like a person who should be able to go to this and read the page. And then finally, that there's like, and maybe I just added this for myself, but we use interaction in a meaningful way. Otherwise, it's just like, we should just like make marketing websites for like the new research paper. We should kind of actually try to help people, like give people an on-ramp to like understanding these things in a more intuitive, deep way by like adding sliders and letting them get a feel for complex systems without having to mess around with like actual equations and math. And unfortunately, I mean, maybe I'm being like too self-critical here, but like, I feel like the canon of like machine learning visualization stuff, after I spent a couple of years doing that, like the best stuff is still the best stuff that it was when I started. And like, why did this happen? And I think there's some kind of things that like basically the same overlaps or same things that happen with news graphics. And then some are like basically exactly the same thing. So there's still the same crossroads or crosswinds with like the attention economy. Platforms have like optimized even harder around keeping you on the page. So like which one is it? Like this visual introduction to machine learning can go like viral on Twitter in a way that like, I think it would be hard for someone just like starting something on a page and posting a link today would be. And there's also some like more subtle parallel crosswinds. So like D3 unlocked all this capacity. Basically all the stuff I used on the explorables page was done in 2018. So like TensorFlow.js lets you run machine learning models in the browser, and it's like taking off, and there's like all this things it seems like you can do with it. And then it's like, well, we kind of get it running and we can't really scale up to bigger models. And then Google loses interest and does other things. So like it's no longer like increasing in capacity in the same way. So a lot of the design space has already been explored. Also like the home run charts, I feel like I kept bumping up against like carcinization, but like I kept remaking TensorFlow Playground instead of like evolving to be a crab. So I made one for like graph neural networks, and then it was like we did one on federated learning. So here's a federated learning playground. And like if you're just like in this design space, you sort of like end up wanting to just like make TensorFlow Playground. But then you're like, well, Sean Carter already made TensorFlow Playground and it looks nicer than what I can do. So what am I doing here? And then there's also some like crosswinds that are like a little bit unique to the machine learning models themselves, or like unique to like what was going on in machine learning. One of them is just like the models get bigger. Like when we have like tiny image models, we can like interactively play with them and see like things happening live and like scrub through things. But as the models just keep getting bigger and bigger, like people are working to be able to run them in the browser, but you can't play with them in the same like visceral way, because you can do like a forward pass and get a token after a second. You can't like run 10 models at once to like see everything happening in parallel, and you're just sort of stuck with like text in, text out. Another one is just like, just looking at, so yeah, this is like 2016, and basically, like the edge of the capacity of what we can do in the browser today. It's like not that we can't do much better than this. One thing that I didn't realize when I was starting with machine learning stuff was just the importance of math. I sort of went in as just like, oh, I did new stuff and there's a bunch of numbers and I just have to visualize the numbers and it'll be good. But with machine learning, there's like a lot of numbers to visualize, and some of them don't make any sense. So one thing that became harder in a way that it took me too long to realize is just that like when you're working with these LSTMs or RNNs, you have a privileged basis. So looking at the individual activations of things is actually meaningful, and you can like group them and see real patterns. But when you switch to a transformer residual stream, the model can like freely rotate that in any direction, and it's basically not meaningful to like look at a single like indice of an activation there, which I spent a lot of time just BERT's residual stream has like 768 numbers in it. And it's like, oh, here's a bunch of ways of looking at those numbers, but it's sort of like a dead end. Other issues with text are that you don't have with like images is we have this like, they actually work as like a pre-attentive thing. So like you can just look at this big glob of like images and you're like, oh, they're all dog ears. And you get that. But like you cannot do that with paragraphs or like even sentences of text. You have to like read them line by line. So being able to like shift and warp space is less valuable when you're working with text. And this is a little bit more subtle, but like text is a discrete space, which means that if you try to do these like deep dream feature visualization things of trying to like activate or maximally activate a single part of the model, you basically just get nonsense with text, and it's not really readable or interpretable. Versus with the feature visualizations, it's like, oh, there's like a dog ear pointing this way, or any number of things. The animal's facing this way, it's facing that way. These are birds. And with text, it all just turns to gobbledygook. And this isn't to say like people are not doing good explanations of machine learning with visualizations. This 3 blue, 1 brown did a couple of long videos that are very good at like explaining the internals of a transformer, but they're sort of violating some of to like do that. I think you have to like violate some of the like assumptions I set out with like the AI explorables. So this basically is still accessible to a wide audience, but it gives up with interactivity entirely, because when you have like a video, you can have the narration tied much more closely to the animations. And it's also, I actually do not know how to make videos that well, but I think it's easier to make a video like this than to actually make like a scrolly telling thing that like does not break on mobile and browsers and like will load all the data. And if you don't need interactivity, maybe you can make a video and it will be easy along these dimensions and make it possible to still reach a wide audience. Another one that's sort of this Karpathy's Zero to Hero like kind of lecture series / collab notebooks. It's also really helpful, and I think very good, but it just gives up entirely on accessible to everyone. It's like, here is like 9 hours of lecture videos and another like 15 hours of homework assignments. And if you do them, you'll like understand how a transformer works. Which is not, the average person coming to a Times website is like not going to do that. But one thing that makes me a little bit sad about this, though, is that in the videos, it's not like he's not using visualizations. It's the visualizations are all static. And there's a lot of them of like, a lot of looking at like loss curves to like understand what's going on in the model, and even more like sophisticated stuff like looking at like the different embedding layers, and even fancier things of like, we have like exploding gradients, and then we can look at these histograms and then figure out how we like need to tune our batch normalization. So when we're working with the models and understanding them, we do use visualizations, but we're not doing any of the like magical interactive stuff, right? And then when we share them, it's still these like baked out charts. Here's one from Martin and Fernando's group that it's like, I guess it's a figure 4, but not a figure 1, but like nicely explains, if you look at it for a while, you kind of get it. And it didn't need to be interactive because they thought a lot about how to like construct the data and make a dense display of it. And I think the thing that I'm like, if I like can't reach like a wide audience with interactive visualizations to explain them, but I kind of think they're useful, still I like feel that in my soul. The thing that I'm like most excited about doing right now is using interactive visualization to do machine learning research and having the output be an actual like thing we have found out about a model. So this was a paper that I did. Yannick was like looking a bunch at image generation models and playing around with different clustering techniques. And we hooked things up to just like, we had our generated images, we embedded them, we clustered them, and we just hooked that up to like a linked hover. And if you looked at like outlier clusters along different dimensions, you get all these like, you can like basically immediately find all these different ways an image model breaks. And I think if I was doing this now, I would kind of, or what actually ended up happening was we like, oh, this is really cool. This is like a useful, neat thing. Let's package this up into like a tool that will run on like Google's infrastructure. And let's go find other teams doing like image generation stuff and let them use this like application to like debug their image models. And then that was sort of like a little bit of a frustrating experience because they're like, oh, this is really cool. And then they never like use it. And you're like, well, why did I build this? And what's the point of it? So we did like some user studies and then put it on archive as like a unit of publishable research. But if I was to redo this, I think what I would do instead, or like try to do instead, is like, instead of polishing the interface and making it into like a standalone application, use this like kind of technique that we think is useful to find out like 4 new interesting things about the model, and then publish just about that. And as like, and then like, maybe if this technique we're using is like actually useful, it's kind of a composable unit that can be dropped into other tools and workflows and people can use it as they need. Basically like pushing us back towards like examples instead of full fleshed out dashboardy workflows that are like all baked out for the user. Let's see. That's Rabble. And yeah, so I don't think this is sort of a new debate at all. This like practitioner as like, we want to use visualizations to accomplish this task versus like kind of like the VISxAI kind of track of like, we want to understand visualizations as visualizations. And after spending time in Petar and being like in this like adjacent to this like HCI community, I think I'm definitely in the practitioner bucket. So maybe none of this is like super critical to like the academic neatness of this conference, but I thought I'd end this talk with like some tips for just like, as a practitioner trying to do research along these lines, like things that I've kind of found useful. And one is just that like, I don't know if this is like exactly the right mental model, but when you want to do like use visualization to like do new research, you sort of have like your output is the minimum of like your visualization skill, your like domain expertise, and like your software engineering skill, which means that like one of the first things I did at Google was like looking at this model uncertainty for like reading tissue slides. And I did a bunch of work at like looking at the model output to like show uncertainty in different ways and try to pack all this like dense information in, and basically went over the design space and tried a bunch of things. And after working on it for a couple of months, I sort of realized that, let's see, this is just like in the last paragraph, maybe I needed to highlight this more. You really need additional information from the model besides patch level softmax values. And there's like some ideas about how you could do that. But I was sort of in this mode of like, the researchers give me like a JSON file and I visualize it for them. And I wasn't getting into this like inner loop of doing work with them. And there's a similar thing with like, I spent all this time that I mentioned earlier, looking at like residual stream visualizations of BERT that just like don't make sense because I'm looking at the individual indices. And to avoid doing that, you really need to find like good collaborators and be able to like make sure your work is just like not that interesting because you've like missed some like critical foundational insight. And yeah, so at Google, there's like a lot of people who had data and were interested in and wanted like a fancy chart for it. And to sort of pick which ones to do it, I'd be like, okay, if you can just give me a JSON or CSV, I will maximize my comparative advantage and like bang out charts for you that like show those things. But that I realized this after a couple of years, it wasn't giving me enough information about their actual task and what problems they were trying to solve. And it wasn't giving me enough like encounters with places that like interactive visualization would actually be useful to like make something. And then more fundamentally, it wasn't letting me immerse myself in their ideas and sort of internalizing them to find out where I could like bend the rules or the data or like make a new kind of data or a new kind of rotation on the data. And I sort of think I fell into this like trap of being like, I really like distill articles have these like sliders on them. And I really like distill. I want to make something as good as distill. So I'm going to make something with sliders on them. And I think a lot of the, like, I could make a more slidery version of this like scaling loss chart, but it's sort of like very information dense as it is. And I actually don't think sliders improve it. And to actually get like insights where you want this, like the thing that we actually like in the distill articles are like new knowledge that's been like distilled down to something good. And the process of getting there isn't making like a polished visualization. Instead, it's more like, here are, this is just like a bunch of Google work that was like unpublished, but like it looks a lot more like I have these like random ideas for things and I'm just like going through them as fast as I can to like look at the research and run experiments and see what works and doesn't work. And just like these big ugly dashboards of trying to get as much information on the page as possible. Yeah, so one thing is, this is like kind of an insane goal of like, I'm just going to show up in your research area and make a better chart and be able to do good research there magically. But I'm excited about like machine learning interpretability in particular, because it's sort of a pre-paradigmatic field where we haven't decided what the actual good things are yet, and we have to lean much more heavily on qualitative results. And so I do think it's like actually possible to do like interesting things here, at least until we have a paradigm for doing things, and then we'll have to move on to like the next exciting thing to work on, so we don't have to just make bar charts for the rest of our lives. Some things I'm excited about for like on a more just like concrete level are this kind of complaining about Claude only being able to like talk back and forth to you, but this is actually sort of transformative because it let me do like near the end of my time at Google, like chatbots like let me actually do more machine learning research and like unblocked me on like being bad at NumPy and JAX. And it can go the other way of like researchers can like actually make good front end charts without having to like mess around with like build steps now. And I think this like capacity augmentation of being able to like keep all the key ideas in someone's head and not being just weighed down by incidental complexity will like let people make pretty interesting stuff in the next couple of years. And like going farther down this, I'm like totally Jeffrey Lit-pilled, like the LLMs should be like making our interfaces. And I don't know how far this goes, is that the models may just keep getting better and do all the research. But if they don't, like concrete things that like near-term things that I like really am excited about, or this is like Datadog, or just like this idea of like, I don't want to like lay out a whole page. I just want to like have a bunch of widgets that are linked to each other, and the researchers and me can kind of like mess around with what they want to look at without me having to write CSS every time. So I had Claude write like a very shitty version in D3, and it's like now in all the Anthropic dashboards. So recommend like just like widgety UIs to like build stuff as you experiment. And let's see. Also, just like the Python to like JavaScript story is like, I'm just like so tired of it, and I think better tooling can work around this. So there's projects like Mosaic and AnyWidget to like make this like nightmare of like being able to like do machine learning things and then do visualization things and kind of not have so much overhead when you do that. If someone wants to make JS, that would be amazing, but I think it might be impossible because you need XLA, but I still have hope someone will do it. And then, yeah, just like when you're working in notebooks, like this like Pense library, it's like, oh, it just shows you visualizations of all of your tensors, and you can look at them and patch them. Other things along those lines are just like transformer lens package of just like not having to deal with so much incidental complexity of like, I need to move activations around in TensorFlow, and this is like basically impossible for me to do in 2018. The David Ball's groups like Neural Net Insight, it's another tool for that. And then also on like just the machine learning side of new lenses for looking at what's going on inside of the model. So this like ways of extracting linear representations, the patchoscope stuff Nada talked about, and then also just like plugging our own book in Anthropic, this like line of research into sparse autoencoders. And I think these tools of like different ways of looking at the model, it feels like progress has been slow, but as we have like different lenses, I think we can use them to like build on top of each other and like iteratively improve them. So I'm optimistic and excited. Thank you.
Awesome. Thank you, Adam, for that whirlwind tour of all the interactive ML visualizations. Super cool to hear your thoughts. Do we have questions for Adam? Yeah. Yeah, do you want to come?
Hey, Adam, thanks. So my question is, given the level of credentialism that we're seeing in industry research, where a lot of people in positions like yours, they expect folks to have a PhD, if you could wave a magic wand and kind of change the way that we run the incentive structure in academia to acknowledge the fact that like 30% of PhD students in computer science don't end up staying in academia, what would you change about the way that we kind of incentivize people, given the fact that there's kind of this disconnect between what's useful and what's publishable?
Yeah, I don't have great ideas here. I feel like at Google, it was like sort of upsetting, like screening interns and having a pile of stuff. And it's like, oh, these people have like a better publication record than me. And I feel like I sort of just wandered in when things were open and before it had all become like hyper optimized. And I do think there's a real downside to that. Like one other like hot take argument in favor of like visualizations being like more boring now is like everyone's gotten like a master's in visualization or like gone to like I don't know, Columbia grad school to do like data journalism. And instead of having this like weird background of a bunch of people coming in from other fields and that like interesting mix, everyone's read the same textbooks. And I don't really like that, but I don't know how to like avoid ratcheting things up. And then yeah, sorry about capitalism, basically.
Maybe that's always the answer. We have another question on Slido that says, do you think there is convergence towards a smaller set of ideas in machine learning and hence also Viz for machine learning?
Yeah, I definitely see that trend in machine learning over the last couple of years of just like, we have a transformer architecture, it works for everything, it scales, so let's keep scaling it and just do that and see if it works, because that beats everything. I don't know if there's like a visual vocab. I feel like we still have so many questions about how information moves around, how it's processed, that I don't know if we have a visual vocabulary yet. Or one thing I think this was a bike shedding meeting we had like a month ago, was the LRE paper here somewhere. Yeah, just getting alignment across everyone working on our little circuits team inside of Anthropic, that we were going to put input tokens on the bottom and output tokens on the top, and use a purple green color scale for negative and high values, because we were tired of visualizations flipping all of those around and being incomprehensible. But other than that visual language, I don't know if we've settled on anything on a field.
Awesome. We have another question on Slido that says, what advice would you give to those new to data visualization research?
Yeah, I guess part of this talk is me arguing that like, I don't know about like data visualization research as a thing. I want to use like data visualization as a task. So if you want to do data visualization as research, I'm sort of like interested and will like look at your like figure ones of paper and click on a demo to see if there's any ideas I can steal, but like I don't know about it as like a thing in itself. In terms of just like if I just want to do like data viz, one take that I also have about like why visualizations are no longer great is that we've like started using a bunch of frameworks to make them, and instead we need to focus on like having like hot reloading and like basically if you're making visualizations, have an environment where you can like edit code and see things update instantly is the most important thing. And it's probably incorrect, but like also don't use frameworks, just use D3 and have everything in one file as long as you can. That's my advice. That's probably not the best way of getting like a career if you want to like pivot to being a software developer, but yeah.
Awesome. Kieran, do you want to go?
Yeah, thanks, Adam. That was very insightful. I was just wondering if over the years you have a favorite visualization that you've made that has like a special place in your heart.
Yeah, I think at least in terms of like this conference, I feel like this fill in the blank one actually hit all the criteria I wanted for the explorables in a way that like none of the other ones like really filled out those three corners. And I'm also a little, I don't know if annoyed is the right word, but I think this is like the correct way of comparing two prompts, of like looking at the difference and like the predicted token values. And it's just a scatter plot, but I don't know why like machine learning researchers don't make simple scatter plots more. So I feel like one trick I've had is just like, I will make you a scatter plot and make it so you can have, you know, hundreds of thousands or like 1 million points on it and all with like linked hover. And that's sort of a boring button to keep pressing again over and over again, but it's like a very useful button, I think.
Cool. We have a live question.
Hi, Henrik here. I was actually wondering, I mean, research is all about like doing good things and then second part, talk about them. And it seems that there's a lot of talking going on at the moment. So a lot of chatter noise, especially in this very buzzing field. Do you have any recipe how to win kind of the shouting contest here? Is it just getting the right label, aka being at Anthropic or being at Google, etc., or is there any other good strategy for like PhD students in not so well-known university or institution?
Yeah, again, this is like, I feel like I sort of got my job at Bloomberg because I just like tweeted out a cool map and then someone DM'd me. But I don't know if that like ecosystem has been like dried up in the same way. I was also like, I will admit to being like frustrated when I'd like post the explorable links, which is like still a Google project on Hacker News, and they get like 4 upvotes. And it's like, if the still was still around and I published this on the Distill domain, people would be excited about this, I feel like, but it's not. And that seems like a real thing. And I don't really know a way of getting around it. I guess looping back to like find good collaborators who can maybe help you with these things, or like do useful things for them to like get yourself into their cycle and then kind of ride their tailcoats is one strategy, or draft after them or something.
Awesome. Yeah. Do you want to?
Hey, Adam, thanks for the talk. I wanted to follow up on something you said about how LLMs have let you like sort of skill up in using in like JAX and PyTorch and all of that. I'm curious, how good are your sort of more machine learning oriented colleagues getting at visualization, and what might that change about like your role about or what we do as they use Claude to get better at like making charts?
Yeah, I don't want to leak any confidential information, so I'm not presenting right now. I'm pulling up a PR that I got last Monday that was adds QK widget, doop doop. Okay, here's a note from like one of my brilliant colleagues with like 300-line PR, mostly written by Claude plus trial and error. I don't really know JavaScript. You, the reviewer, could be the first human to understand this code. It might need an overhaul. And I was like both excited to like see that they had like done this experiment and added this like new thing that we were like flowing through to the model. But then also the code like did not make sense and was going to like not work at all. So I like them not being blocked. But then it's like also making a pile of work for me to do of like, they have these like pile of visualizations they've had Claude make, and then I'm like manually rewriting them. But then I'm also like, well, what am I here for after, you know, Claude 4 or whatever comes out, and you don't really need me anymore. So I guess we'll see how that goes.
We have another in-person question.
Oh, one more like bullet point on that. I guess that's like why I'm excited about these kind of like tools for making it easier to pass information back from JAX to, or from like JavaScript to like Python and back and forth, and like good visualization primitives of just like making good bones and composable primitives that the LLMs can like remix at will is sort of like the goal. Yeah.
Hey, Adam. Thank you for really great presentation. And as a designer working in data visualization, I'm interested in having your opinion in what is the best way to assess what works and what doesn't work in this field. How do you go with that?
Yeah. I try to like keep my like diva impulses like under wraps a little bit, but the like idea of doing a user study, or I'm trying to find of doing a user study when I first did it was like sort of like, no, I'm the designer here. I know what's good and it's not, and I picked it, and like I'm gonna have to like go interview people and write down what they said and like report that. It's like, no, but that's sort of like sufficient for doing like just like shipping things and getting things done. But if you like actually want to have a science of things, I do think you do need some sort of validation loop. So I don't know.
Okay, well, on that, I think we might wrap up questions. If anyone else has questions, you can post them to Discord. But thank you again, Adam, so much for that talk. I think we all had a lot of fun today. Great, so we'll just quickly close the session here. Thanks again to Adam. And we'd like to close by giving out our Best Submission Awards. So drum roll. Thank you. The winners are Can Large Language Models Explain Their Internal Mechanisms? And the Illustrated AlphaFold. Our reviewers, yes. Our reviewers were both really impressed with how both of these submissions took these really complicated concepts and were able to use visualization to make them so accessible to the reader. So congratulations to you both. What next? If you enjoyed today, reach out because we'd love to keep VISxAI going, and we're always looking for fresh perspectives to make this workshop better. And with that, VISxAI 2024 has officially come to a close. Thank you again to my fellow organizers, everyone who submitted, our program committee, reviewers, all of you watching on YouTube and Zoom, and all of you in this room. It's been a blast.
What an event. Thank you, Angie, for running this.